Hi everyone, I'm Richard. Today I'm going to talk about software testing, reflecting on some of the things that I've learned. When I started out writing software, the idea of testing it using other code was super daunting, especially in C, which is what most of my code was written in at the time. Since then, I've been on a journey to be both introduced to and independently learn about various ideas and techniques around testing the code I'm working on. Along the way, I've had many conversations with other developers where we express the concern that testing is hard. Test-driven development, or TDD, is so much harder than test after development, also known as eventually consistent testing. Do any of these resonate with you? My test suite is more code than the code being tested. My tests are more complicated than the code being tested. My mocks break all the time. TDD is too hard. I can't predict the code that I'm going to write. I'm not confident the code is going to work without testing it manually. It can be hard, it can be complicated, and it can be frustrating. As a more experienced developer, I have worked through a lot of that difficulty and frustration and come out the other side. And I'd like to reflect on some of the things that I've experienced and learned along the way. This talk is broadly split into two parts. In the first, I will talk about some things that I believe are making testing harder than it needs to be, and in the second, I will talk about some things I think we can do to make testing easier. I'd like to talk a bit about the conversations we're having around testing. If there's one thing we developers do well, it's be bad at conveying ideas outside of code. Disagreeing about the meanings of specific words is the distillation of that. So many times in so many environments, I've had conversations about testing that have gotten bogged down or have ended ambiguously because we have different internal ideas about what very common words and phrases mean. For example, if I asked you to define what an end-to-end test is, I can guarantee that your current, previous, or future software collaborators will have learned and internalized subtly or even wildly different definitions. Through a vast and very long game of telephone, we've all come to differing understandings of what testing is and how to do it. And this can lead to frustration and even conflict, which stems from that difference in our internalized expectation of what we're trying to achieve compared to somebody else. Similarly, if I asked you to define any of unit, integration, or functional test, I can also guarantee that you'll have different definitions to mine or any number of other developers. So what is a unit in a unit test? Is it a function? Is it a class? Is it a module? Is it a business rule? Going right back to the very earliest definition of unit testing, a unit was defined by Kent Beck as a unit of code in isolation. Code tests were not necessarily well-sized or focused, and not well isolated from each other in scope or even execution. Sometimes tests would leak state and affect other tests, sometimes causing them to pass incorrectly or causing them to fail unexpectedly. So this is where unit testing started, but through that game of telephone I mentioned, the meaning has been altered and some important aspects of the message lost. Many developers will assert that a unit is defined by some specific code shape, like a single function or a single class. Personally, I find a slight variation of Kent Beck's definition to be very helpful. Note that I don't define it by an amount of code, just an isolated behavior. How that behavior is defined is entirely dependent on the specifics of the application in question. We need to be flexible in allowing as little or as much code to be covered by the test as needed to isolate that behavior. tests can and should test several classes working together if that is what is needed. Another very common point of confusion is having conversations where developers will use the terms end-to-end or integrated to encompass their own idea of a set of constraints on a test without expressing those constraints and leaving as implied some characteristics of the tests that distinguish them from unit tests. What are the ends, though? Are they a front end and a back end? Are they a start and an end of a workflow? Popular tooling exposes some of this confusion. For example, the Angular project cookie cutter, Angular CLI, it creates projects with an E2E folder, short for end-to-end, which contains browser-based user interface tests. The implication here is that end-to-end is driven through the UI, backed onto a mocked backend. The Angular E2E docs muddy the waters even more by including the phrase, also known as integration testing. More recently, I've been developing React applications, and searching for React E2E testing results in many different opinions about what that might look like. Do you automate a browser? Do you mock out your backend? Many opinions abound. If you start talking about integrated testing, then things get even more variable. As I've already mentioned, for some people, E2E means integrated, and vice versa. For some people, an integrated test can only consider a fully deployed environment with the application, its dependent services, and any databases required to support them. These are often manually run tests and require a ton of work to set up. For others, a set of services in a mesh is sufficient to test specific interactions, though still with no mocking. Perhaps all dependent services except the database are mocked. For a slowly growing number of developers, integration testing is done through contracts, using a tool like Pact to declare interactions between consumers and providers, and to verify those tests are still valid over time. As I've mentioned, for some developers, the testing of a user interface over a backend is an integrated test. I've also encountered some more fine-grained definitions stating that a test that encompasses presentation layer over business logic is integration. Further, I've had developers who have a very specific concept of what a unit test is claim that any test that crosses a module or class boundary is an integration test, or even anything outside of a single function. But is any of that helpful? Having those hard boundaries and rules internalized, that will invariably only lead to confusion, frustration, and even conflict with other developers. Probably the clearest demonstration of this wild difference in opinion is the testing pyramid, first presented by Mike Cohn in 2009. It was a good idea and simple in presentation. The basic premise is that more effort should be spent in the fatter sections of the pyramid. The labels are reasonably straightforward. Unit and UI tests are reasonable concepts to agree on, but the service layer is interesting. It refers to larger components or higher level functionality. Cohn's example is to test the addition or subtraction feature of a calculator without poking at the buttons in the user interface. But still, we'd have to agree on what the boundaries are of a service layer test. But then do an image for testing pyramid and marvel at the difference in opinion present in the varieties of pyramids. The variation can encompass such things as different types of testing, manual or automated. Testing for purposes that I've not mentioned thus far, such as acceptance testing, which is about meeting contractual obligations placed on software so that it be fit for its intended purpose. Some diagrams break out layers, so service could become a variety of different things like component, integration, or API tests. Yet another pyramid introduces software lifecycle phases into the breakdown of tests, with alpha and beta testing. The pyramid's vertical axis now covers both complexity or cost and waterfall project completion stages. Some pyramids go so far as to assign percentage numbers to the slices of the pyramid, as if to say that the visual slice size isn't enough. You must also measure the number of tests to ensure that 6% of your tests are workflow tests, which are somehow different to integration tests and business logic tests in ways that aren't necessarily clear. This is all derived from a very limited selection of the hundreds of pyramids that come up in a quick search. And all of them are slightly or wildly different. One version I like, beyond Mike Cohn's original, is by Steve Fenton in 2015. Instead of using words like unit and integration that we can't agree on, it talks about qualities of the tests. In his diagram, malleability refers to the tests hindering changes to the code being tested. So that gave me an idea. What if we stop trying to shoehorn our thinking into word-shaped boxes and all the confusion that arises from that, and rather we step back and think about what broader qualities of tests make them good or should be avoided? Much like the Zen of Python provides us with aphorisms to allow us to reflect on the code that we are writing, perhaps there is something similar that can help us in testing that code. I found this list of suggested goals of testing written by Kent Beck, and it partially inspired this talk. It talks about test isolation and testing behavior and not structure. Kent does explain that not all of those goals of testing apply to all types of tests. For example, he says monitoring abandons being predictive and to some degree being automated. I think the list has merit, and I've drawn upon it for inspiration, but I have some thoughts of my own as well. As an aside, I find in general that there's 3 levels of memorability for me when I'm trying to recall complex sets of ideas like this. The first, and the most popular with professional trainers of management, process, Scrum, etc., is the mnemonic acronym. Things like solid, acid, true, smart, ideal, invest, spider. They're great words. I bet you all have an understanding of what ACID might mean in general terms, like it's a good, reliable database, but what does the I stand for? What does it really mean? Or from solid, you might be able to remember that the L stands for the Liskov uncertainty principle, which isn't its actual name. But if you're like me, then you're stumped if you can remember what Liskov was on about. That is, the actual meaning behind the L. The second tool of memorability, as presented by Kent just now, is but he's by far not alone in this, is a list of words like inspiring, specific, and composable. It can be easier to remember these specific words, but after a while the meaning intended by them is lost. What did Kent mean by composable? The final, and by far the most memorable for me, is phrases. I can quote the Zen of Python to you, and I can expound on each of those aphorisms because, as a series of words, their intent is much clearer. Beautiful is better than ugly. Explicit is better than implicit. Simple is better than complex. Complex is better than complicated, and so on. Now, it might be that you are a little hazy on the deeper meaning behind complex is better than complicated, but I'll wager it's still more memorable as a concept to think about. And just on that last one, I would like to aside in my aside because it would be helpful as I continue to talk about tests. A simple thing is easily understood. It is plain, unadorned, and generally encapsulates a single concept. A complex thing is composed of simple things in a straightforward combination, with clear dependencies, hopefully in one direction, between the parts. A complicated thing is comprised of many interconnecting parts with no clear dependencies between them. Understanding these definitions, it follows that simple is better than complex, which is better than complicated. I'll be coming back to this idea of simple over complex over complicated more during this talk. So with that in mind, I present to you a set of aspects of testing to contemplate. I will now explore each of these in turn. Going right back to the whole thing about the beginning of unit tests, this bears repeating. Tests must be isolated from each other. A unit is a unit of code in isolation. Tests should always be isolated so that they do not impact other tests. This was a foundational goal of unit testing. They should not alter permanent state or modify the testing environment. No test should ever rely on another test having run to itself pass. Tests that are isolated from each other will return the same result regardless of the order in which they are run. If nothing changes, the test result should not change. Running the test 1 or 100 or 1,000,000 times will achieve the same results. Tests should never leak state and affect other tests, perhaps causing them to pass incorrectly or perhaps causing them to fail unexpectedly. Once you have isolated tests, they should be exercised constantly. At a minimum, during development, before commit, after commit. They should be exercised by a computer without the need for a human intervention. This removes the need for a human to remember to run the tests. Tests should be sensitive to changes in the behavior of the code under test and not to the structure or detail of the code under test. Ideally, our unit of testing should not be a function, it should be an isolated behavior. Testing an isolated behavior will improve your test suite's malleability, its ability to continue to pass regardless of the underlying implementation. What is a behavior though? It could be calculating the total value of an order based on the line items received. It could be calculating the duration of a train running between two stops. If an order can sometimes have a discount applied to it, that is a separate behavior that should be tested. That is, don't have one test that tests the total with and without a discount. If you need to test multiple similar behaviors, you can use a tool like PyTest's parameterize. It allows you to invoke a function multiple times with different inputs. So here we are testing the calculation of the order total with one line, with several lines, and with a discount applied. We write one function which expresses the general method of the test, calculating the order total, and then provide a number of behavior scenarios in which it must work. If the behavior changes, the test result should change. Tests should not change their result if the implementation of the code changes. If you do not witness a test failing, you can never be certain its success is valid. As a general practice, the first thing you should do is write enough of a failing test to express a behavior that fails, then write enough code to make that test pass. and then repeat. This is test-driven development in a nutshell. Once you're happy with the scope of your test and code, refactor as appropriate to clean up the code. This process is sometimes known as red-green refactor. The tests start out red, which is failing. They are made to become green through the writing of sufficient code, and then you refactor to make the code pretty, or otherwise better. One common stumbling block here for a lot of developers is the very first step of TDD, writing a failing test. Often they stumble saying, "But I don't know what the code is that I'm writing the test for." Something that can help here is knowing that your test doesn't need or want to know about the details of the implementation. Indeed, knowing too much about the implementation is to be avoided. Rather, if you're unsure what the code is going to look like, start with the absolute most basic assertion about the functionality that you're writing. For example, if you're writing a brand new system that must manage trains which travel around a network over time, which might also have a bunch of other requirements like crewing the trains or moving cargo around and so on, it is probably overwhelming. Start small. Start with a train and a single property of the train, making up what you think will be a nice API as you go along if you don't already have one defined. So in this example, invented to put on this slide, we write a test which creates a train, moves it around the network, and then we ask it to calculate its duration. Even if this isn't the final API for how trains work, it's a good starting point. It will fail. And that's okay, because now you can start writing some code, and just enough code to make the test pass. And now you've also got a test that will always ensure that you're calculating the duration of trains correctly, regardless of the implementation of how that works. Tests shouldn't execute too much code or too many behaviors. This helps keep them reasonably isolated, but also prevents having large, complicated, and fragile tests. Ideally, tests should exercise only one behavior. But how that behavior is defined is entirely dependent on the specifics of the application in question. Tests can and should exercise several functions or classes working together if that is what is needed for the behavior. Focus does not mean that you should restrict your test or isolate it to a specific quantum of code, like a function or a class, or even a single module. That level of isolation is not feasible, and attempting to do so will almost certainly result in complicated code, or tests that contain far too much mocking. If you do find that your test, even when focused on a specific behavior, requires significant setup of dependencies, then perhaps the code being tested is doing too much and itself is not well focused. It could be that you're testing too much of the implementation rather than the behavior. Where possible, tests should exercise one behavior that is simple, or if not simple, then of low complexity, but hopefully never complicated. Tests should not have assertions about different behavioral expectations. If a test fails, it should fail for one reason, and not prevent a separate test assertion from being made. Again, PyTest's parameterize can help greatly here. Tests should never have conditional branches. Make a new test, or use parameterize to express multiple scenarios. I haven't talked about mocking yet, and some folks equate isolation with a need for mocking, so let's talk about that, and dependencies in tests. When I talk about dependencies, I'm referring to both third-party code you're pulling in as a package, but also the internal components of your application. For example, the data models that your business logic depends on, or the business logic that invoked by your user interface. The term test double was coined by Gerard Mezaros as a way of talking about mocking, stubbing, faking, and all that, without those confusing words. To make remembering the idea of test double easier, think stunt double. It's a meta term that we can use to encapsulate a wide variety of methods to replace dependencies in test code so that you can invoke your application code to test it without invoking the dependencies as well. There's many words that are used to refer to specific doubling techniques. Fake, fixture, dummy, stub, mock, spy. As with other terms in testing, people have varying ideas about what they mean. But broadly, there are several qualities that are present or absent in doubles. They can provide input to your code which is not used. Perhaps you're just filling in unused function arguments. They can provide input to your code as a dependency would. Here, your code needs specific data to operate, and you're providing it something that's got enough of the shape of the dependency to work. They can accept output from your code as the dependency would. Your code is going to invoke the dependency with some data, and you need that to work. Sometimes you want it to record that invocation or spy on it. They can statelessly translate output to input based on a rule set. That is, given your code invokes the dependency, it expects the double to respond to it with some specific data. Your double now has logic coded into it. Your double can provide assertions regarding the output received. Now the double has validation rules coded into it, and it's primed to check the data your application sends to it to check there's only expected behavior. Now, rather than have the rules coded directly in the test, a developer must also look to the double to know all of the rules. Finally, a double may implement state-driven behaviors of the dependency. Here you're basically rewriting the dependency. Those last few qualities, where the double is getting more complicated, should be avoided wherever possible. Simple, immutable doubles, often called stubs or mocks depending on who you talk to, allow you to replace a dependency of code being tested with a double whose interface looks and behaves like the surface of the dependency. Complex mutable doubles, called mocks or fakes depending on who you talk to, extend that idea by adding mutability, having their own state that can change during the execution of the test. This greatly complicates their design by encapsulating aspects of the implementation of your dependencies into the tests. You would want to limit the use of these complicated doubles in your test suite. By the way, a database is a complicated mutable double. If you find you're using these complicated doubles for even seemingly core tests of single behaviors, you may be in trouble and need to step back and look at your architecture. Perhaps it is too tightly coupled, too complicated. I should note, if you find you want a high-level test of your application that covers a number of behaviors and a large portion of the code, then using complex, mutable doubles is most likely going to be the only way to achieve that goal. A great library for providing simple immutable doubles is called Pretend. I will be making use of it in some of my examples to come. It works like this. Here, x will be an object with a single attribute, country code, which has the value US. Unlike the Python standard library mocks, x will not respond to any other attribute or method. Nor does it have any methods for making assertions about what you accessed. If you want to add a method to the stub, provide a function to it. This allows us to provide simple functions that do or don't take args and provide input back to our application code. Magic mocks, like those found in the standard library, are never a good idea. Magic mocks will automatically mutate themselves in response to the code under test, adding attributes or even callable methods. These objects frequently result in tests falsely passing in the face of typos or other coding errors. Doubles should always be explicitly coded to the shape of the dependency being replaced. And when you must use doubles, keep them as simple as possible. Don't re-implement your dependency just to double it. Monkey patching is a technique commonly used in tests to replace the implementation inside a dependency with some double so that your test can be isolated. This is a simple example of monkey patching in action. The simple bookface implementation has a tight coupling to the bookface library. This makes it more complicated. It is now composed of complicated things, but it also becomes more difficult to replace that dependency in tests. We have to monkey patch the external module to replace its implementation of the dependency. This is dangerous. It might have unexpected side effects, and it's fragile to changes in that module. We can use a technique called inverting the dependency to change the code to look like this. Simple bookface now accepts a service called graph, which provides the functionality the application logic needs, but decouples us from the tight coupling to the third-party module. Note that there's no import of the bookface library any longer. The implementation of simple bookface is much simpler. Your high-level application code, or bootstrap code, would be responsible for creating an implementation of a graph service that could be provided to simple bookface. In the test, we no longer perform that fragile and complicated mocking to replace the dependency. We can create a simple stub instead. So this is a simple example, and while the motivation behind making this change probably makes sense to you, you're most likely going to be wondering how to apply that approach to your own larger, more complicated application. I'm going to now take some time to introduce a great architectural trick, which is to think like the onion does. Or more specifically, the onion architecture, by Jeffrey Palermo, and tweaked and improved by many others since then. This is a simplified version of the architecture. At your application's core, you define the data domain in the most primitive form you can. Think basic Python data types and classes that have no knowledge of data outside of themselves except for referring to others by ID. You surround that data domain with your application logic, which uses the domain and services provided by external APIs. This is sometimes known as the policy layer, but I find that term confusing. The user interface and API code exist side by side in the outer layer, neither depending on the other. This could also be thought of as the I/O layer, where your application interfaces with other things, people or systems. It is sometimes known as the infrastructure layer, which refers to the facilities and services that the application needs. This architectural approach has many benefits, one of which is that it allows the application to scale very cleanly when new features are added. It's super nice for agile development, where whole features can be added, altered, and removed as the application matures. But there's also concrete benefits for testing, which is why I'm talking about it. So, how do we make the onion work, really? Now there's a bunch of code on this slide, and I'll let your eyes wander over it for a bit before I walk through it. There are 4 different sections of code here, representing components of each of the parts of the onion. The domain, which defines our data as very simple classes. The application, which implements our application's logic, like calculating the total price of an order from its component order lines. The UI, which displays an order by ID and date with its calculated total price. Note the dependency container that we use to obtain our orders store. I'll be coming back to that. And APIs, which interface to our complicated external dependencies, in this case requests, to provide the functionality that the application needs. One of the most important aspects of the onion approach is that the code in the outer layers depend on the code in the inner layers and not the other way around. But Richard, I hear you say, that application logic is using the API from the outer layer. Well, it might look like that at a glance, but there is no import from that outer layer into the application logic. The application logic could use any orders store as long as it's compatible. The application logic has the dependency it needs provided to it or injected into it from outside. Similarly, the user interface doesn't have a hard coupling to our requests API code either. Instead, we decouple it using a dependency container. In this code, the dependency container is just a dictionary. In practice, it might have additional safety rails, which I'll come to. We can register any implementation of orders store we like with that container, including in tests, which I'll also come to. Rather than have hard coupling between our code and its dependencies, we have it ask for the dependencies it needs. This allows us to both decouple our code from specific dependencies, allowing flexibility in our implementation and deployments, and provides doubles very easily in our tests, where we can plug them into the dependency resolution system. In this case, it's just a function argument. In typed languages, we might formally declare that orders store implements some specific interface. Python has typing now too, so we can do this. The application logic can code a protocol which declares what its requirements are for an orders store. We declare that protocol to include 2 methods, one called byId and the other one called getLines. The ellipses are used to indicate that there's no functionality in the protocol. Any orders store now provided to the application code will be checked by a type checker to ensure we're providing the correct thing. Pywrite is a great Python type checking tool that you can run on the command line and also has fantastic support in Visual Studio Code. We can also use a typed dependency resolver too, like tres or tray from PyPy, to ensure that our implementation of orders stores are valid too. Tray validates our registration of dependencies and provides us with their type when we resolve them. Going back to the example though, without all that typing malarkey, which is super useful but also super optional, we can see how the data model and application logic are now testable without needing complicated dependencies. We've decoupled them. Creating some orders and order lines to test the application is easy. We need a minimum of doubles to test now. Something I want to reinforce is that the inner layers be as simple as possible. You might be tempted to interface to your database right there next to your data classes. ORMs make this super easy, but they're a trap. The database is a horribly complicated external dependency. It belongs out here and should provide services which can drive your application like our orders store did. If you need to run a whole database, or even a pretend one, to be able to run your unit tests, then it could be that your architecture is too complicated. On the subject of dependency injection, in Python, the PyTest testing framework uses dependency injection for its own test fixture management, which greatly simplifies writing tests. But we also have libraries like Dependency Injector and TRES, and others. This has been a whirlwind introduction to the onion architecture, dependency injection, and inversion of control, and I recommend searching up some articles to learn more. It's a lot to take in, but my intent today is to introduce the ideas as potential ways to work through architectural complexities that can make testing harder than it need to be. Okay, moving on. Tests should run as quickly as possible. This encourages frequent, if not constant, execution of your test suite. If your UI tests are speedy, then sure, use them constantly. But if they're not, do them, but make them optional. Good test running tools will give you the ability to rerun tests constantly while you work. This is great because you very quickly get feedback when you break something. If you only run the tests once you're done, then you may have to go back through hours of work to figure out where you broke things. You can use a tool like PyTest Watch to continually run your PyTest suite while you work. Here, PyTest Watch has noticed that the code changed and it's rerun the tests. But I broke it. But I was told about it immediately, which is super good. It's also a good idea to run PyTest over multiple CPU cores to get both an added speed boost, but also sneakily check that your test isolation is working. If a test fails because it's running on a separate core, then something is definitely leaking state in your test suite. If confidence is only achievable with slow tests, still do them. A fantastic example of that is using a browser-based test to exercise your website application. Now, I can already hear the groans of the audience who have probably attempted to automate Selenium in the past. Fear not, dear audience, the world has improved. Much cleaner and more reliable frameworks have been built on top of Selenium, which, to be fair, was only ever designed as a browser automation tool. Frameworks such as Cypress and Selenium Base now make writing tests much simpler and more reliable. This is an example Selenium-based test, which attempts to log in to our application using a test login, verifying that we see the user login correctly. Just think about the volume of lower-level tests that you'd need to write in order to get the same coverage of functionality as this test. The confidence that this test provides is huge. Tests should never require explanation. They should certainly have a stated purpose, which is usually encapsulated in their name, but tests should be readable and understandable for the reader, invoking the motivation for writing this particular test. Test failures should be obvious and informative. Tests should be easy or easier to write relative to the code being tested. Things that might hinder understanding of a test. Mutable or otherwise complicated mocks. conditional branches, tests that are not focused. Having said that, if the test just reiterates the code being tested, then there's a good chance you're testing the implementation. Perhaps consider whether you could broaden the test to cover more code. And I'll repeat myself, there should never be conditional branching in a test. If the reader has to reason about the behavior in a test, then it's just too complicated. Finally, if all of your tests pass, then the code under test should be suitable for production. If the tests pass, then any new work or refactoring should be considered safe. This encompasses both the number of tests, that is, the coverage, and the quality of the tests. I'm not going to put a specific number on what I think good test coverage is, and say that you should attain that level also, because confidence from test coverage will vary considerably from project to project. A project I'm currently employed to work on has around 60% coverage, and that's pretty good. A side project that I've open sourced has 100% coverage, so I have confidence that I'm not going to break it when picking it up to apply some community pull request. As for quality, well, hopefully that's covered by the other aspects of testing that I've talked about today. The practice of test-driven development contributes greatly to this confidence. A number of other testing methods can also contribute greatly to confidence. Smoke tests, in particular, can ensure that your application passes a limited set of very high-level tests that ensure that critical functionality is present when deployed. For example, once deployed, your smoke test can ensure that the front page of your website has expected content, and perhaps that a user might log in. Keep such tests reasonably simple. Don't necessarily test a complicated interaction where perhaps a specific user can log in, navigate to their orders page, select an in-flight order, and modify it. That particular interaction might require significant investment to implement and be fragile to simple changes in the user interface design. Those more complicated interactions should be covered by other tests run continuously during development. The smoke test exists to ensure that the deployment of your application is working correctly. My final word is to not take any of this advice as inflexible rules. Getting fixated on hard rules about testing has only caused us confusion. Consider these thoughts that I've presented. Reflect on how they might apply to your efforts. I do hope some of this advice today will help you achieve confidence in your testing.